Yeah, Udit, you can start. Udit, have you started? Your voice is not
No,
audible.
no. I have not. Okay, so should I go ahead? Okay. How many members are there?
You can start.
Okay. Okay. So you guys have seen what are the various components used, uh, which we are going to use in SLAM. Like you have seen what is visual odometry. You have seen P3P, PNP algorithm. You have seen ICP odometry, bag of visual words, and post graph optimization. Now we are going to see an EKF, an EKF also. So now we are going to see how we are going to use all these things to make a complete SLAM picture. Okay, this picture this picture tries to represent the complete SLAM pipeline using most of the state-of-the-art SLAM systems. Like there might be some parts which are used in one SLAM system and other parts which might be used in other systems. But like this pipeline represents like most of the complete SLAM system. So we would first start with sensors. So you might have RGB sensor, RGBD sensor, and you might also have wheel odometry coming from your robot. So then your sensor framework will provide the raw sensor output like the frames, image frames, and the poses, which are wheel odometry poses. So first we will do image processing. So once you get this images, so then you will do first a SIFT or ORB. So whichever is fast or whichever suits your need, you will do that type of feature extraction. So once that feature extraction part is done, then you will pass this extracted features along with their descriptors to this data association block. In this data association block, basically two things happen. First is feature tracking, which we also call as uh, short-term data association, and there is something called loop closure, which we call long-term data association. Why it is called short-term data association? Because like the features are tracked between consecutive or first or third or first and fourth, but not that long. So that's why it is called short-term feature tracking, uh, short-term data association. And in loop closure, we always want to close the loop when robot has revisited its starting point again. So like there might be differences of 1,000 or 2,000 frames between the pairs of loop closure. So first in feature tracking, we do this optical flow, which will say like if you know features in your first image, then if you want to know what are the corresponding features in your second image, then you can do optical flow to track where those features have moved. And in loop closure, you will do basically bag of visual words, which will say given a query image, which is the most relevant image in your database. So once you get two image pairs from bag of visual words, then you want to calculate the transformation between those two images or between those two robot poses, because finally we want to use those transformation to correct the drift accumulated in your robot poses. So you will do ICP algorithm. And then once you do this feature tracking and once you know what are the features in your first image and your second image, then you will try to do visual odometry. In visual odometry, you can use PNP algorithm. Like if you have 2D to 3D correspondences, then you can calculate exact robot pose, exact camera pose. And if you have like only two 3D point clouds, then also you can do ICP odometry and calculate the relative transformation between two camera poses. So from this, you will get the RT estimates between consecutive robot poses. Uh, now, now if you just have this visual, only visual sensor, then you are done. But if you have like wheel odometry also, then you can do this EKF fusion. And the main advantage of EKF fusion is that like the final covariance in the robot estimates will be less than of either of the visual odometry and the wheel odometry. So visual odometry might be certain about some like noises in some direction, and wheel odometry might be certain about noises in some direction. But their fusion, which you will do using EKF, will be the best of two. So once you get this odometry from visual odometry, and once you get from wheel odometry, then you can do EKF fusion to get a better estimate of odometry. There are some SLAM packages which also use this local bundle adjustment. As Shubodh has earlier mentioned that uh, bundle adjustment provides better accuracy than post graph optimization, but it is at the same time computationally expensive. But you can afford to do local bundle adjustment around your newly inserted key point to get a better estimate. Like let's say you get a current image and you have a robot and you have a map which the robot have mapped. So you can do local bundle adjustment around your current keyframe to get a better estimate of your current keyframe. So that is called local bundle adjustment. So now after all these algorithms, you get a very good estimate of odometry. But we know, however good your odometry is, it is bound to drift because noises in your sensors, noises in your measurements, or not exactly using the exact measurement model or exact sensor model. So there will be some drift or noises. So in order to correct those drift, you will use this loop closure thing. So like it is used basically in like long-term mapping. It plays a huge role. So once if robot revisits its same position, then you will correct the drift using loop closure. So output of this front end basically will be keyframe poses and the loop closure pairs. So in the backend optimization, as we previously covered, you will do like you will use this algorithm, LM algorithm basically, 11 Marquardt's algorithm, and you might also use some robust cost functions if you want to if you want to take outliers into account, then you can use robust cost function as well to to correct the drift. So basically, as someone yesterday asked me, like what are the clashes between odometry and loop closure pairs? So yeah, in order to correct those clashes only, you can use this backend optimization. Here we will give a higher weightage in the cost function for the loop closure constraints, and we will give a lower weightage to odometry constraints. Then you will get a solution which will be which you initially want to know. Like you initially want to know the probability distribution of X given you in a post graphs formulation. So uh, once you get this optimal robot poses, then you can use optimal robot poses and local point clouds to generate and assemble point cloud. Like corresponding to each robot position, you have some robot a local point cloud from robot camera position, and you have this optimized poses in world fixed frame. So then you can assemble this point clouds to get assemble point cloud, and at the same time you have this pose graph robot poses as well. So this is a complete slam thing, like where you also have a uh, robot positions and a map of the environment at the same time. So this picture is taken from a taken like this picture is taken from RTEM map thing, which we ran on our lab data set. So here we used wheel odometry and RGBD sensors. So yeah, this blue thing is robot poses, and this white thing are the floor regions, because we are looking at the top view of this generated map. Okay. So yeah, basically here only I am mentioning each of the components in detail. Okay, so yeah, feature extraction. And as earlier mentioned, like you get odometry constraints, which are basically which is normally distributed. Okay, and yeah, this is the formulation you want to maximize. Like you want to maximize this probability distribution in a postgraph formulation, and this is the complete SLAM formulation which you want to know. Like you want to know the map, you want to know the robot poses given your odometry commands and your sensor measurements. Okay, now classification of the complete SLAM pipeline. So this picture tried to encapsulates all the major algorithms which have been developed in the past by researchers working in SLAM. So this picture is taken from Nico Sundarov thesis, also mentioned in references also. Okay, so currently, so we are main. So currently, like most of the state-of-the-art SLAM systems, like RTAP map SLAM and ORB SLAM, try to use this G2A formulation. Uh, and okay, so I will start from left side, but I won't going any like deeper in any of the concepts, but just saying. Okay, so you can do so slam problem is divided into like what is your input type or what is your output type. So your output map can be occupancy grid or some or features or like or point clouds or like just the robot positions, or based on the sensors you can use multiple sensors like monocular camera, stereo camera, RGBD camera, or lidars. Now it can be basically static or dynamic. We are basically concerned about the static slam. And algorithms can be Bayesian filtering algorithm, which people used to do in past. Basically, they also Bayesian filtering also don't take into account this loop closure things, which is easily integrated into this optimization framework. And also this like optimization algorithms uses the uh, sparsity in your Jacobian and your Hessian matrix, which we earlier saw that like Hessian matrix is quite sparse. So we can use linear algebra techniques to deal with the sparse matrices. So then that also make it quite fast. So that's why people use this postgraph optimization formulations. And also this optimization formulation can also be divided into non-linear least square methods, relaxation methods, linear methods, or stochastic gradient descent methods based on whatever optimization algorithm you want to use. So like if you are doing just SGD to solve the cost function, then you want to use this. But like as I earlier mentioned, people want to use this Leavenworth-Markowitz algorithm, which is implemented in this G2O library. Okay. Okay. Now SOTA matrix. Okay. Shubham,
Yeah.
you can share the screen. Yeah.
Yeah. Yeah, so we will briefly look at a few SOTA methods, state of the art methods. So one of the first, like the first ever monocular visual slam system is MonoSlam. It's called MonoSlam by Professor Andrew Davison. So that was the monocular slam. That was the first setup which has actually showed using a single camera, using a single monocular camera, you can actually localize in your environment and also sparse mapping. So this is what the first SLAM system consisted of. The front end was very sparse feature point tracking, very sparse because we have seen even now it is very difficult. If you use, we have ORB SLAM. Yesterday I have briefly described how we use ORB SLAM, and that has more priority compared to Swift because ORB is faster, even though it's not as accurate as Swift. So that is why back then, since it was like 13 years back, it was very sparse feature point tracking if you wanted real time. And then these were the early SLAM days, as Udit has just explained. You can see the years here. In the early SLAM days, EKF was used, Kalman filters and filtering methods were used. Eventually, we have not covered particle filters, but around 2000 to 2005 particle filters were used. And then right now, graph-based methods are the most popular. G2O, ISAM, GTSAM. There are a lot of work being done even now. So this is the most recent set of methods. So as you can see here in the early SLAM methods, Kalman filtering was the standard way to do backend. So it employed Kalman filtering as backend. So what it used to do, as in you must have studied yesterday, that so it only given previous state of the camera and current landmarks, it'll tell you what is the current state of the camera. Mean and covariance is done using Kalman filter, as you have seen yesterday. So that is what it does at every time step, and we have seen how your Markov property says if I know current state, that encapsulates all the information that I have captured in the past. So I need just current state and my current observations to make my current. I mean, you need your previous state and current measurements to determine your current state. So I'll ask you a question. It's an interesting question. So there's this. I hope you can see this video. So over here at around this time, you can see these ellipsoids, right? Can someone guess? You can see these ellipsoids, right? These are landmarks. I'll tell you what each thing is. Firstly, this is camera. Camera is moving in the world, and it is doing very sparse point load. So each of these things is one feature point, and it is using those feature points, it is tracking its position. So can someone guess what these huge things are? And firstly, tell me what those huge things are. And we just observe that they are initially too big, and then they are becoming small. Look at this. If look at this, now this is too big, now it's becoming small. It's just too big, it became small again over here. Can firstly someone answer what are those huge ellipsoids that you see? I'll just pause at, yeah, what is this ellipsoid? Can someone guess? It has something to do with, yeah, it's covariant.
It could be. I mean, they are trying to guess it, and as the guess becomes accurate, the ellipsoid becomes smaller.
Yeah, that is it. That's it. So yeah, as you said, ellipsoid is the covariance, and initially, as it's very uncertain in this direction, it's in like camera's z direction, it's very uncertain. So that's why you have a big ellipsoid here. That meaning it's very uncertain. Eventually, as the camera moves and sees it again, that will kind of shrink. And that meaning I have estimated that more certainly. So that is the monocular SLAM system, first ever monoslam system. Now Udit will cover ORB SLAM. Do you want to share your screen, or you can ask me to scroll?
Okay. Okay, so ORB slam. So first of all, why we call it ORB, orb slam? Because basically it uses orb features to do most of the things, or you can say all of the things where you need features. So you need features and their descriptors while you want to do for visual odometry. You also want to use them when you are doing long-term data association, like called loop closure. So ORV SLAM basically reduces the computational burden by using all features at every place. So their dictionary, bag of visual words dictionary, is also made up of ORB features. And once you calculate ORB features to do visual odometry, those ORB features you can also use to do the query against the database images. So everything is comprised of ORB features. And ORB features are like quite accurate. Like they are very much accurate compared to like if you use some simple Harris detector type of things. But at the same time, they are not as much as computationally expensive as like Swift and surf algorithms. The other point, okay, so the second salient features of ORB Slam is that it divides the whole pipeline into three major components. Like, uh, yeah, okay, yeah, it divides the whole pipeline into three major components, like tracking. The second component is local bundle adjustment, and the third component is loop closing thing. So this ORB Slam builds on its predecessor PTAM, which came in 2007, and this ORB Slam paper came in around 2015. So the the idea is borrowed from PTAM that you can separate out uh, tracking and mapping thing. So that's why around that time only the idea of front end and the back end came. Like you can do tracking and like you can. So ORB Slam proposes that you can do tracking, you can do local bundle adjustment, and then you can do loop closure and post graph optimization in three different threads. So so yeah, so it is like so like this paper has like a high impact in this slam community. So first of all, I will start with this tracking thread. So this tracking thread is responsible for detecting the ORB feature points and also to calculate the robot your camera movement using PNP algorithm. The second local bundle adjustment algorithm does this local bundle adjustment around the current key point. Like if you have a current key point ki, then all the keyframes connected to that ki will be used for local bundle adjustment. So basically, what is keyframes? So keyframes, the concept of keyframe is that in order to reduce redundancy, like you are getting input images at okay, so, okay, so 1 second. Uh, well, choose a feature get extracted. So like there's a question like, is there any Swift slam? So you basically, so is there a question in chat is that basically we have Swift slam. So yeah, we don't have uh, in particular Swift slam, but you because you don't want to use Swift in visual odometry because you want to do yeah, because you want to be real time, so you don't want to do shift detection for visual odometry, but in data association, you can use feature detector like in long-term data association, which you don't want to do. So there is one thing which ORB Slam also exploits, that you need to run this tracking thread at a very high frame rate, but you can like you are fine if you run this loop closing thread at a smaller frame rate because you don't do loop closure at every like at every instance. Only when a new keyframes come which is similar to the previous thing, then only do you do loop closing thing. So there you can do shift matching. Okay, so yeah, so coming back to this ORB Slam, so it also coined up the idea of this okay, okay. Coming back to this ORB Slam, it also coined up the idea of this co-visibility graph. Co-visibility graph is nothing but whatever your current keyframe is, and whatever the frames earlier frames which robot has seen are more like are the most similar to this form the co-visibility graph. Like you have a graph, and there would be an edge uh, between two nodes. If the number of features, like there would be a threshold like 20 or 50 is more than that, then there will be edge between those. So if you scroll down, so yeah, so this green thing, so the figure B is basically a co-visibility graph. So you add this new keyframe, and if there's a threshold exceeding like 50 features, like more than 50 features between this current keyframe and the previous frames, then there will be a edge in this co-visibility graph. And you do this local bundle adjustment in around in a local region in this co-visibility graph. So you know a current keyframe, and you know all the keyframes connected to this current keyframe. There you only do local bundle adjustment. And the third thread is loop closing thread. So in loop closing thread, they coin up this term called essential graph, which is basically nothing but a covariability graph, but with fewer edges. So like there, the criteria uh, for a edge to exist between two nodes is high, like instead of 50, let's say 100. So yeah, so as you can see, essential graph is looking quite similar to covariability graph, but like it is a sparse thing. So here you do here you do full post graph optimization. This red edge in the essential graph is basically the loop closing edge, and and you have generated this essential graph out of this covariability graph. So here we will do full post graph optimization. So yeah, this is ORV Slam.
Yeah.
Shubodh, yeah, you can continue.
Can you repeat what spanning tree is?
Okay. Okay, so first of all, we formed a minimal spanning. So the concept of spanning tree is is used here. Like you have a co-visibility graph, and you want to generate a minimum spanning tree of this co-visibility graph. Basically, like there should be minimum number of edges from, like if you are at point A, and if you want to reach like at point E, so like there can be multiple paths between them, but the concept of minimum spanning tree here says that like there should be edges should be minimized such that each point should be connected to each point, and the number of edges should be minimum. Like whatever links are here in the causality graph, they should also exist in the spanning tree, but yeah, but the number of links should be less. Like it should be minimum as possible. Like it is a general concept borrowed from data structures. So yeah, I think you guys are also familiar with this.
Okay, okay.
Okay. Yeah.
Yeah. So, so far you have seen in both the cases in MonoSlam and ORB, we have seen sparse feature tracking. I mean, you have only so yesterday we have seen there are two methods of doing visual odometry, right? First one is using feature point based methods, and the second one is direct methods, where you consider the whole image. So the previous two methods that you have seen are like the formal methods, purely feature point based methods, but there are also dense methods. In addition to this, there are lots of other dense methods also, some of which are very impactful in the Slam community. I'll be covering SVO for today. So it stands for semi-direct visual odometry. It is called semi-direct. It's not called direct. We have seen what direct means yesterday. It is because it is a combination of both key points. I'm not using descriptors here. I'm only using key points to identify what are interesting points. And around that key point, I take a certain block and then I apply some direct method there. I can consider all the pixels around that particular point and I apply some direct method over there. So instead of direct matching the whole image, they do it for a block around the key points. So it's like a trade-off between. So why do we use direct methods and why do we use feature points? Like what are the advantages of each? Is that feature point methods are fast, as in so like your direct methods use the whole image information, and feature point methods are fast in the sense if you want to do something like local bundle adjustment, it will be helpful over there. So you want a trade-off of both. If you want to, this method is kind of the best of both worlds. So instead of doing direct matching of the whole image, which will be very computationally expensive, they only do it around one particular, like a few key points that are given by my some feature detection algorithm, and so it is very fast. It is about 400 frames per second, and it is, since it is very fast, it can be used in UAVs, drones, and also handheld AR VR devices. You, even if you move your head, tilt your head very fast, it's able to accurately localize yourself. And so one thing about this semi-direct visual odometry, it itself, in the name itself, it says it's visual odometry. It is not a complete SLAM pipeline because they're not doing backend optimization or loop detection. So that means as you move, even if it's decently accurate, over long periods of time, it is bound to increase. The cumulative error, the error is bound to get cumulative and it will increase. And so you cannot correct it if you re-observe some location. So it is just a visual odometry pipeline. You have to use this in conjunction with some backend optimization method like G2O or ISM, as he was describing previously. Yeah, that is about SVO. Udit. Udit, are you there? Udit? Yeah, Udit, are you there?
Yeah, I'm sharing. Yeah. So RTAP map is a classic solution to RGBD SLAM. So initially it came as a solution to RGBD SLAM, but later it also incorporates other type of sensors. And like RTAP is quite successful from the engineering point of view. Like it is also currently in development, or like most of the SLAM systems has like their developers has stopped working them. Like I can say of ORB SLAM, but the developers of RTAP map SLAM are continuously developing it for different type of sensors. So currently it supports like most of the sensors available in the market, like a stereo sensor, monocular sensor, RGBD camera, IMU, and lidar. And if there's a new sensor like the real sense or something would come into market, then also so it is quite popular package if you from the engineering point of view. And also it provides output in various type of formats, like point clouds, occupancy grid. So people also use RTAP maps for navigation as well. Like if you want to do path planning, so it provides output in terms of occupancy grid as well, which is useful for like your planning algorithms, I think, which we are going to cover in later lectures. So there you will see what are planning algorithms, and if you have occupancy grid as output, then you can do planning as well. So RTAP map builds on ORB SLAM, and okay. RTAP map RTMap builds on ORB SLAM, and it uses most of the techniques. Like it used the essential technique of there should be one tracking thread and there should be one mapping thread. So this is what RTMap also incorporates, and it has other components as well as like backend optimization, back of visual words, and feature-based visual odometry. RTAP map also provides the support for a multi-session mapping. So multi-session mapping is, you can just say like it is a fancy and name for like loop closure detection. Like first of all, you will each robot will build a map in its own world fixed frame. But whenever two robots sees image from another data, like map from another environment, then a RT estimation would be done using ICP algorithm. And then if you know the RT estimate, then you can merge these two maps. So then both maps will come out. The final answer would be from a fixed file frame from either of these two maps. So it also provides multi-session mapping. Yeah, Shubham.
Yeah. Yeah. So we will briefly be looking at the current state of SLAM and the future in which direction it is heading towards. So one of the promising directions that many of the uh, like big names in SLAM are working is semantic SLAM. You, it has multiple names. You can call it semantic SLAM, topological SLAM, spatial AI, but all of them are essentially more or less what we'll be covering today. as in the fundamental concepts. So let us start with a more general question. Yesterday also someone was asking regarding the loop closures. So there are two aspects. How do humans see? So the first aspect is how do we navigate? Let us say this is your first day at your college, and you are trying to search for your let's say yes some of your class. Now the first few days you still struggle to remember, or at least the first 1 2 days. You ask around. You need a priori information, or as you move around, you ask other people for help, and then you end up there. But ultimately you have to revisit that place in order to remember the place. Without, if you want to navigate by yourself autonomously, you have to revisit that place. That is kind of the funda behind loop closure. Someone is asking yesterday, why do we use loop closure? So even humans navigate that way. Now secondly, coming to to how humans navigate. When you navigate, we don't really look at feature points. We do not navigate at a feature level. We rather look at rooms, we look at objects, we look at people, and then accordingly we estimate our own position. Okay, if this let's say you're in a car, and the buildings are moving past you, and if they are too fast, then you are moving too fast. And you actually you don't look at points, but you look at something like more semantically rich representations of the world, such as, let's say, objects or agents. So as you know, there have been lots of advances in deep learning, things like semantic segmentation, instance segmentation, pose estimation. All of these are very useful for SLAM. So if you can see in this particular image, till now we have only seen SLAM. SLAM in its, like, we have talked briefly about sparse SLAM. We have mentioned dense SLAM. So this is kind of what would be the output of dense SLAM. This is just the these what do you say? These red ones that you see here indicate the camera pose. I have shown you how camera is represented yesterday. So all of these are camera poses, and or localization in other words. And the map that you see is this actual, like, the whatever world you have captured, the 3D map. This is your mapping part of SLAM. Now, in addition to this, what semantic SLAM is you are also classifying each object in your environment. For example, this is a pillow, this is a wall, this is a floor. So in addition to that, you have another layer, localization, mapping, and then semantics. So that is called semantic SLAM. There's a lot. All of these are very recent works. In fact, this is 2020. This is also maybe over in the past 1 2 years.
I have
All
a
of these
doubt.
works.
So why is semantic slam uh, groundbreaking? Because we know that there have
You
been
will come to that.
classifiers. Okay.
We'll come to how semantics helps SLAM and SLAM helps semantics.
Okay.
So yeah, this is another very illustrative image which I've taken from this paper called 3D Dynamics in Graphs. This is 2020 paper. Again, this is also at level 1. You have a metric semantic mesh, and then as you move upwards, you are trying to capture higher level information. In layer 2, you have objects and agents, and something like humans, chairs, any other objects. And then you have layer 3, which is places and structures. And then rooms, and then buildings. So this is sort of a hierarchy, helps a lot even for post-graph optimization. In fact, our IICRA 2020 accept, we worked at level 4, you could say. So we were modeling our whole trajectory in the form of individual rooms or individual places. Let's say let's say bedroom, and then hall, and then some other lab room, and then optimizing based on that, optimizing our backend based on that. And in fact, so when I said our paper, I meant Udit and I, the extra 2020 paper that we had. And other paper that we're working is at layer 2. Basically, we are trying to, operate at a level of objects and find out, it's kind of ICP for level of at level of objects. So it's very powerful. If you have that sort of rich semantic information, you know what is useful information and what other useless information you can throw out. For example, if you're navigating in the environment, maybe you don't have to use all the information in the world in order to localize yourself. Maybe your floor is not very useful because it's not very, it doesn't have many features, or it's always there. You want to see what are major changes in the environment. So for those sort of things, this hierarchy helps. Again, this is another way of representing. This is from a recent talk given by Andrew Davison. So that is what the levels that I was talking about. First one is robust localization. Second is dense mapping. This is the dense map and localization that you have seen. The third level that we are talking about is semantic understanding. And this is like current state, today's state of SLAM. So you are doing SLAM at a level of objects and places rather than mere points and pixels. So Andrew Davison calls it spatial AI, this sort of SLAM systems hierarchy, and each level is interconnected. Like level 1 helps level 2, level 3 helps level 1. All are interconnected and help each other. So semantics help SLAM and SLAM helps semantics. This statement is taken from this paper called Past, Present, and Future of SLAM. You can read that for a more elaborate discussion. So how do semantics help SLAM? Firstly, let's say you are able to do instance segmentation. You're able to do semantic segmentation and segment out humans in the world. So dynamic SLAM, we have only talked about static SLAM, right? All your environment, if your environment is static, we can do SLAM to a good extent. It is it is quite accurate. But the problem is when it's too much, when the environment becomes dynamic, it is a huge problem, because all of your algorithms assume your environment is static. It is bound to fail. It is bound to not be as accurate. So one thing you could say about how to use semantics would be, now let's say you are able to segment out a human being or other dynamic objects. First of all, you are using some classification, like using deep learning. You're applying some classification, and okay, in this particular image I have some humans, so I have to be careful. So that itself is an analogy I can think of for human beings is, let's say you are walking alone on a footpath. So you will not, be very conscious, right? But if there, let's say, some human being sitting over there, there's a dog running around, you immediately become aware and navigate accordingly. You are more, you would be slower, but you would want to be more accurate. You do not care about efficiency or something, but you are more concerned about not hurting anyone else. So that sort of that sort of understanding can also be incorporated in SLAM. Let's say the moment you see dynamic objects in the scene, you can compromise on a bit on your let's say robot speed or robot's efficiency, and focus more on ensuring you are moving in proper direction, even if that comes at some other cost of efficiency or something like that. And also, let's say, using semantics, you can maybe filter out dynamic objects in the scene. So that is how semantics can help SLAM. You can also, let's say, there's already things like object tracking. Instead of doing feature tracking, you're tracking your whole object, as in you're tracking the pose of your whole object. That is also at a level of objects. Okay, that's about of like a vague idea about how semantics can help SLAM. Now, how can SLAM help semantics? So when we do, we have been doing. I mean, you must have done ran an individual image. Like in typical deep learning applications, what do? You take a bunch of images, you train them, and you run them again during test time. But each image is an individual entity, as in you do not have any relation between each image. For example, in your typical applications, let's say your Google Photos is, I don't know, it's detecting certain objects in your image. Google Lens, let's say you have taken a photo of your plant and you want to know what plant that is, but you're just taking one photo. And if you have a correct model, like you have trained a particular model to identify all sorts of plants, and today you can actually do that. You can open up your Google Lens phone and see for yourself. It will be able to predict what that plant is, and that is pretty accurate. But in a let's say a robotic setup, you do not need to treat every image independently, because a lot of the information that you see in present image is already it has a lot of common overlap in the previous image. So it doesn't make much sense to do a forward pass of the entire image every time. So that way, when you have a when you are in a SLAM setup, you are navigating forward. I have explained that photometric laws and warping equation. You can actually warp it to the previous image. You can warp the current image to the previous image using your localization or pose obtained from your SLAM system, and then only look at points which are which have changed. Instead of trying to process the whole image once again, you can only look at what have changed, and that's how like localization part of SLAM can help semantics. So that is one, I have briefly tried to give a understanding about current state of SLAM and in which direction it's heading. So yeah, and there's a lot of promise in this. In fact, Jan LeCun, again, in the recent IIITH talk, he has given a plenary talk. You know Jan LeCun, right? The Turing Award winner. He's one of the three guys who has won Turing Award for his contribution to deep learning. So he was one of the, you know, he has given one plenary talk during IIITH 2020, which was like 5 days back. Today's June 11th, right? It was, I think, on June 2nd or June 3rd. So he said the deep learning revolution in speech recognition took off in 2011. In vision, it was in 2013. In NLP, it was in 2015, and in robotics, it is now. It is now as in 2019, 2020. So yeah, there's a lot of promise of these applications in SLAM. But first of all, you need to understand what SLAM is. That is what we have been trying in the past 7 sessions or 9 sessions. You have to understand first what SLAM is, and then you can understand what deep learning is, because deep learning is essentially a tool you are employing on SLAM. So yeah, that I think marks the end of this lecture. I hope it was not too long. Okay.